Imagine you are floating in the quiet, inky dark of space. Everything is calm, everything is peaceful, and everything is going pretty well for you, considering you are suspended in the universe's biggest no returns accepted zone. Then somewhere in the distance, space itself seems to ripple, almost like it is taking a nervous breath. And from that breath forms a shape, not really a shape at all, but more like a cosmic idea with gravity issues. A black hole, the universe's most dramatic door with no exit. But here is the strange part. As frightening as black holes seem, as much as they are painted as the ultimate destroyers of anything unlucky enough to wander near them, they behave in a way that feels oddly alive. Not alive in the sense of keeping a diary or complaining about Mondays, but alive in the way they grow, adapt, and influence their environment. They are like cosmic creatures that never stop eating, growing larger with every meal, and quietly shaping the universe without ever lifting a metaphorical finger. It feels almost wrong to compare one of the most extreme objects in the universe to something living, but the similarities pile up fast. Think about living organisms for a moment. They need energy, they take in resources, they grow, and they change over time. They are shaped by their environment, and in turn, they shape the environment back. Now, picture a black hole doing something eerily similar. It pulls in energy from its surroundings. It consumes matter. It grows in mass and size, and its very presence can reshape whole neighborhoods of stars. The universe may not hand out official birth certificates, but if it did, black holes would be the strange children scribbled in the margins with a note that says, "This one is going to be interesting." Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift toward sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now let's begin. There is something deeply compelling about this comparison. When we think of black holes, we naturally imagine the scary part, the falling in forever, the stretching of matter until it is thinner than cosmic spaghetti, the absolutely unforgiving gravity that says, "You had a good run, but this is where the universe stops being polite." Yet beneath all that intimidation, there is a kind of quiet, patient purpose to them. They are not chaotic disasters spinning wildly out of control. They are consistent, predictable, methodical. They behave like a creature that never needed instructions because instinct will do just fine. The moment a black hole forms, its story begins with an appetite. It cannot help it. The universe wrote its rule book without leaving room for picky eaters. Anything that drifts too close, gas, dust, light, planets, overconfident space travelers, is pulled into a gravitational hug that never ends. But this hunger is not random. It is a slow, careful, gravitational pull that works over immense spans of time. This makes black holes feel less like destructive monsters and more like cosmic compost bins. They recycle the universe, one unlucky piece of matter at a time, and transform it into something else: mass, energy, power, influence. And the influence part is where things really start sounding alive. A black hole does not just sit there like a cosmic vacuum cleaner waiting for someone to drop crumbs. Its gravity can organize matter around it, shaping the paths of stars and the flows of gas. Entire regions of space can revolve around the mood swings of this single invisible point. In a way, it builds its own environment, not through intention, but through the sheer strength of its presence. It is like that one friend who never asks for attention, but somehow becomes the center of the group chat anyway. The funny thing is, black holes do not even look like anything. They are invisible, defined not by what they are, but by what they stop you from seeing. The only clues you get are from the things unfortunate enough to circle them or fall into them. That is the universe's version of studying an animal by watching the trail it leaves behind. And this invisible, quiet, gravitationally unreasonable thing behaves like it has cravings and instincts. It expands its influence with every cosmic meal, and it does not ever seem to get full. If the universe offered a buffet that stretched across millions of years, a black hole would politely say, "Yes, all of it." So why does something so mysterious behave like it is growing with intention? Why does this cosmic mystery feel like it is a creature evolving, adapting, and consuming across the ages? This is the puzzle that pulls people in just as powerfully as gravity pulls matter. And the more we learn, the stranger and more wonderful the whole idea becomes. A black hole is not alive, not technically, but it grows, it changes, it reacts, and it transforms its environment in ways that feel suspiciously familiar to anything that needs energy to continue existing. In the vast stillness of space, where stars burn out and galaxies drift like cosmic tumbleweeds, black holes remain the quiet engines of growth that never stop pulling the universe forward. And maybe, just maybe, calling them alive is less about accuracy and more about capturing the awe they inspire. After all, if something walks like a duck, quacks like a duck, and bends space-time like a cosmic heavyweight champion, maybe the universe is telling us it is close enough. If you want to understand why black holes grow the way they do, you have to start with the moment they arrive in the universe, not born in any gentle hospital room sense, but blasted into existence through one of the most dramatic cosmic events possible. A star, once proud and radiant, suddenly caves in on itself like it has just remembered every mistake it has ever made and decided to implode out of embarrassment. This collapse is not an ordinary fall. It is gravity calling in every favor it has ever been owed. The star's core becomes so dense and so cramped that it essentially says, "Fine, I will be a black hole now," and the universe quietly makes room for its newest resident. The surprising thing is how tiny these newborn black holes can be. For all their intimidating reputation, most begin humbly, barely larger than a city, yet holding more mass than multiple suns, squeezed into a space small enough to give even the toughest cosmic engineers performance anxiety. Imagine something with the weight of a few stars, but the vibe of a very confused infant that immediately develops an instinctual craving for matter. It is the universe's most dramatic baby photo. But just like living creatures, these young black holes do not all start life under the same conditions. Some are born into crowded stellar neighborhoods filled with gas, dust, and leftover debris from their parent star's final explosion. Others materialize in much emptier regions, where the only thing nearby is the occasional lonely particle drifting by like a cosmic tumbleweed. These early surroundings matter tremendously. A black hole's first environment shapes its entire future, its growth, its behavior, and even its personality if it had one, which thankfully it does not, because the last thing the universe needs is emotionally needy gravity pits. A newborn black hole's first meals are usually the leftovers from the star that created it. When a star collapses, not everything falls inward neatly. Much of it gets thrown outward in a spectacular explosion that would win every award if the universe hosted a fireworks competition. Some of this material eventually slows down, cools, and drifts back toward the baby black hole. This is the cosmic equivalent of a parent leaving snacks on the table, making sure the little one has something to munch on while figuring out how to exist. In these early moments, the black hole's growth begins shaping its gravitational personality. The more mass it swallows, the more its gravitational pull intensifies. The more intense that pull becomes, the easier it is for it to grab new material. This creates a fascinating, almost biological pattern. Black holes that start life with a hearty supply of nearby matter tend to grow faster, stronger, and more aggressively. Those that start life in cosmic deserts remain small for astonishingly long periods, sitting quietly in the dark like they are waiting for a delivery that never arrives. There is something almost poetic about this early stage. Even though black holes are not alive, they experience something that looks suspiciously like an early developmental period. Their surroundings mold their future. Their first meals influence their eventual strength. Their early experiences decide whether they stay modest or balloon into massive giants. It is like cosmic childhood, except with fewer cartoons and far more gravitational overconfidence. As these new black holes adjust to existence, they begin interacting with the space around them in ways that shape how they will continue growing. Their gravitational reach is small at first, pulling mainly on immediate surroundings. But every bit of matter swallowed, even a passing wisp of gas, adds to that reach. Growth at this stage is slow and steady, more like a gentle simmer than the roaring cosmic feast people imagine. And this early pace matters. Black holes that grow slowly early on tend to remain calm diners throughout much of their existence. But those that gorge themselves from the beginning often become ravenous, pulling in matter with an intensity that sets the tone for the rest of their cosmic lives. There is also something quietly dramatic about how much is determined in these first stages. A young black hole formed from a star several times larger than our Sun can end up on a path to becoming a heavyweight, especially if it is located in a region rich with material. But a black hole, born from a smaller star placed in a sparse region, may remain tiny forever, hardly ever encountering anything to feed on. It is the universe's version of socioeconomic inequality, except you cannot fix it with better policies or motivational speeches. Even more fascinating is how the collapse itself influences the newborn black hole's internal structure. The spin of the original star is encoded into the black hole like a cosmic fingerprint. If the star was spinning quickly, the black hole will inherit that fast rotation, which can dramatically affect how it pulls in matter. A rapidly spinning newborn black hole can twist nearby spacetime into a swirling dance, making material hang around longer before falling in, creating a more prolonged early growth phase. In contrast, a sluggishly spinning black hole tends to pull things in more directly, leading to a quicker but less complicated feeding pattern. So in these early ages, black holes are more than just cosmic leftovers. They are active, developing entities shaped by the chaos that created them. Their mass, spin, neighborhood, and initial meals all combine to determine who, or rather what, they will become in the universe. And much like living things, their earliest moments matter more than anyone might expect. A black hole's future appetite, its reach, and its long-term influence all begin in these first quiet, invisible steps. By the time a black hole leaves this early phase behind, its growth trajectory is already set. Whether it will go on to become a quiet wallflower of space-time or a gravitational superstar depends entirely on these formative, star-born beginnings. If black holes had a motto carved into some cosmic family crest, it would probably read, "I pull, therefore I am." Gravity is their defining trait, their signature move, their entire personality condensed into one unstoppable force. But for black holes, gravity is more than a simple attraction. It behaves almost like a kind of cosmic hunger, a craving that deepens with every bite of matter they capture. And the more they eat, the more powerful that craving becomes. This is where black holes stop feeling like mere objects and start resembling self-reinforcing processes, the universe's most dramatic example of a feedback loop that never learned the meaning of moderation. The idea begins with how gravity works in extreme environments. Normally, gravity is a polite participant in the universe. It keeps planets in their orbits and stops your cereal from floating away. But in the region around a black hole, gravity becomes something entirely different, intense, relentless, and unapologetically clingy. It does not gently attract matter the way a star or a planet does. Instead, it drags space itself inward, warping the fabric like a bedsheet pulled too hard at the corners. Anything unfortunate enough to wander into this warped region begins sliding toward the center. Not because it is being swallowed instantly, but because space-time is slanting like a giant funnel. This slanted space-time is the beginning of the hunger metaphor. Think of gravity as the black hole's biological impulse. It is not a desire in the emotional sense. Black holes do not write poetry about the matter they have lost or gained. But it behaves very much like an instinct. Their gravitational pull is not static or fixed. It grows. Every time a particle falls in, the black hole becomes more massive. Every time it becomes more massive, its gravity strengthens. Every time its gravity strengthens, its reach extends farther into space, sweeping more matter inward. This is the ultimate cosmic loop. Eat, grow, repeat. This cycle is not only efficient, it is alarmingly elegant. No living organism could dream of such seamless growth. Black holes do not get indigestion. They do not need rest. They do not worry about overeating, because overeating is the entire business model. The moment something crosses their event horizon, the point of no return, its mass becomes part of the black hole. There is no gap, no digestion phase, no waiting period. It is an instant investment in future gravitational strength. If growth were an Olympic sport, black holes would win every time, mostly because they would secretly pull the other competitors into their event horizon and eliminate the competition entirely. One of the strangest and most fascinating aspects of this gravitational hunger is how it behaves at a distance. Even far from the event horizon, the black hole influences its surroundings subtly, altering the paths of dust clouds, streams of gas, and the occasional wandering star. These objects might not be anywhere close to falling in, but they feel the tug. It is like the gravitational equivalent of smelling food cooking in another room. You are not eating yet, but you are thinking about it. And the more massive the black hole becomes, the farther its gravitational aroma spreads, drawing in more material over time. Another layer to this bizarre appetite is how gravity affects time itself. As matter approaches a black hole, time slows down relative to the rest of the universe. This means, from an outside observer's perspective, anything falling into a black hole seems to take longer and longer to reach the event horizon. In a strange way, it makes the black hole look like it is savoring every meal in slow motion, even though from the falling object's point of view, it is plunging inward without hesitation. Gravity becomes not just a force, but a distortion that shapes how the black hole interacts with everything around it, stretching time as effortlessly as it stretches space. This hunger loop becomes even more dramatic when matter starts piling up nearby. Gas drawn toward a black hole does not always fall straight in. Instead, it can accumulate in a swirling halo around the black hole, a region where particles crash into each other, heat up, and emit energy before eventually spiraling inward. This swirling region feeds the black hole slowly but steadily, adding to its mass bit by bit. And as it grows, its gravitational appetite strengthens yet again. This feedback process ensures that once a black hole starts growing, it becomes harder and harder for anything nearby to escape its influence. Gravity snowballs. The tiny black hole that began its existence as a compact stellar remnant gradually transforms into a region of space with gravitational reach far beyond what its humble beginnings would suggest. It becomes not just an object, but a dominating force, shaping the motion of everything nearby like a gravitational monarch. What makes this even more extraordinary is that there is no built-in limit. Stars can only get so big before collapsing. Planets can only accumulate so much material before their shape and stability break down. But black holes have no upper boundary. They can grow indefinitely as long as the universe continues to drop matter into their gravitational domain. This open-ended growth potential sets them apart from anything else in nature. They are the ultimate demonstration of the phrase, "The more you have, the more you get." except applied on a scale that would make galaxies rethink their career choices. And at the heart of it all is gravity behaving not just as a force, but as a kind of cosmic appetite, an instinct that intensifies with every morsel of mass consumed. Black holes are not alive, but their hunger behaves like something that evolves, something that escalates, something that turns the act of growing into the very mechanism that fuels even more growth. They are the universe's most compelling reminder that sometimes the simplest rules, pulling things inward, can lead to the most astonishing outcomes when pushed to their extremes. If black holes could set a dinner table, accretion disks would be the fine china, beautiful, swirling, dangerously hot plates spinning at impossible speeds. They are the cosmic dinnerware that never stops moving, never cools off, and never gets put away because the meal is always ongoing. From far away, an accretion disk looks like a glowing halo wrapped elegantly around a region that should not shine at all, which makes the entire thing wonderfully ironic. The darkest objects in the universe are surrounded by some of the brightest structures ever observed. An accretion disk begins forming the moment matter tries to approach a black hole, but arrives with a bit of clumsy sideways momentum. Instead of falling straight in, the material begins orbiting, caught in a gravitational standoff between falling and circling. Gas, dust, shattered remnants of ancient stars, and even entire clouds of cosmic debris all join this rotational parade. At first glance, it looks like chaos, a messy swirl of everything the universe had sitting in its junk drawer. But the longer the disk spins, the more organized it becomes. Particles rub against each other, collisions heat the material, and over time the disk flattens into a surprisingly elegant thin ring that circles the black hole with hypnotic precision. This swirling disk becomes the black hole's feeding mechanism, a cosmic conveyor belt that delivers matter inward gradually. But nothing about this process is gentle. Friction between particles generates extraordinary heat. As the disk tightens and the material spirals closer to the event horizon, temperatures rise to levels that would make even the sun question its work ethic. Gas heats to millions of degrees. At those temperatures, atoms lose their electrons, turning the disk into a glowing plasma, a kind of cosmic soup that radiates light with wild intensity. This is why accretion disks shine so brightly, because they are literally cooking. Now here is where things get absurdly impressive. A well-fed accretion disk is so luminous that it can outshine not just stars, not just clusters of stars, but entire galaxies. Imagine a single black hole surrounded by a bright ring of swirling gas, producing more light than hundreds of billions of suns combined. It is the universe's equivalent of one diner at a restaurant ordering so much food that they become the brightest thing in the city. These hyperluminous systems, powered entirely by accretion disks, are known as quasars, cosmic lighthouses so radiant you can see them from across the visible universe. Which is even more impressive when you realize that the black hole at the center is not shining at all. It is the disk doing all the work, while the black hole sits there like a silent partner taking all the credit. Inside the disk, the physics becomes even stranger. As matter spirals inward, it loses energy through heat and radiation, causing it to move closer and closer to the black hole. This process is slow at first, but accelerates as the material tightens toward the center. Think of it like water circling a drain. The outer regions move lazily, swirling with a relaxed pace, while the inner edges spin with frantic speed. Near the black hole's edge, the material can orbit at a significant fraction of the speed of light, a level of enthusiasm no dinner plate should ever have. And it is not just speed that gets intense. Magnetic fields develop within the disk, twisting and snapping like cosmic rubber bands. These magnetic fields can channel some of the material into towering jets that shoot out from the poles of the disk. These jets come from the disk, not the black hole itself, and are so powerful that they can stretch for thousands of light years, piercing the galaxy like cosmic searchlights. Even though the jets are not part of today's chapter, the fact that accretion disks can launch matter outward while simultaneously feeding inward is proof that they are far more than just passive rings of material. They are dynamic engines converting gravitational energy into light, heat, and motion. The structure of the disk also changes over time as the black hole feeds. When the black hole is hungry and material is plentiful, the disk thickens and glows fiercely. When the supply dwindles, the disk thins, cools, and fades. It is like watching a campfire shrink when the fuel burns low. Except in this case, the campfire can engulf entire stars without blinking. The shape, color, and intensity of the disk all act as clues about how actively the black hole is feeding at that moment. But perhaps the most intriguing aspect of accretion disks is how they act as the black hole's gatekeepers. Everything that reaches the event horizon must first pass through the disk. This means the disk regulates the flow of matter, determines how much heat is produced, and influences how fast the black hole grows. The disk is not just a feeding platform. It is the entire digestive system, controlling the pace and intensity of consumption. Despite all this activity, the disk itself exists in a delicate balance. Too much turbulence, and the disk can puff up and become unstable. Too little, and the inward flow slows to a crawl. The most efficient disks sit in this perfect middle ground, where collisions are frequent enough to produce heat and radiation, but not so violent that they disrupt the structure. In its own chaotic way, the disk maintains order, keeping millions of individual particles moving with the grace of a cosmic ballet. Accretion disks reveal a side of black holes that is surprisingly elegant. They are not just silent devourers, but centers of vibrant, swirling complexity. Through these glowing, dynamic rings, black holes announce their presence to the universe, not through words or movement, but through light that travels billions of years to reach us. When you see an accretion disk blazing across space, remember, the brightest lights in the universe come not from stars, but from the dinner plates of cosmic darkness. If the universe ever hosted a cosmic potluck, black holes would show up with wildly different appetites. Some would stand politely near the snack table, nibbling on the occasional crumb like they forgot to bring their reading glasses and cannot quite see what is available. Others, the supermassive ones, would arrive with the energy of a competitive eater, inhaling everything within arm's reach and then casually asking when dessert is served. It is one of the most puzzling things about black holes, how two objects built from the same basic idea can end up living drastically different lifestyles. Some remain forever modest, barely growing at all, while others swell to millions or even billions of times the mass of the sun. The universe offers many mysteries, but few are as dramatic as the divide between the quiet hermits and the galactic monarchs. The biggest difference between these two black hole lifestyles is location. Ordinary stellar black holes tend to drift around in the outer suburbs of galaxies or remain tucked away in regions where matter is scarce. These places are cosmic slow food zones. There is not much traffic, not much debris, and definitely not enough gas clouds to keep a black hole well fed. It is like opening a restaurant in the middle of a desert. No matter how hungry you are simply not going to see a line forming at your door. These black holes have the gravitational equivalent of picky eating forced upon them. They are not choosing to remain small. They simply never encounter enough material to grow dramatically. Meanwhile, at the center of galaxies, the situation is wildly different. Galactic centers are bustling, noisy neighborhoods filled with swirling gas, dense clusters of stars, and regular incoming streams of raw cosmic material. If the outer galaxy is a sleepy rural town, the center is a metropolis with 24-hour restaurants. A black hole placed here is not just lucky. It is destined for greatness. It has access to a constant supply of food, whether it be drifting gas clouds, wandering stars, or debris pulled inward by the overall gravitational dance of the galaxy. It is like being placed at the heart of a never-ending buffet with no closing hours. This simple difference in environment fundamentally shapes the growth of black holes. Stellar black holes born in isolated places can go billions of years without eating anything substantial. They may occasionally capture a stray particle or a small wisp of gas, but nothing that dramatically changes their mass. They remain passive observers of the universe, waiting patiently for something, anything, to wander close enough to be caught. And the universe, being the vast and unhurried place that it is, does not always provide. But for the black holes in galactic centers, life is a completely different story. These regions are gravitational magnets for gas and dust, funneling enormous amounts of material inward over time. Clouds collide, compress, heat up, and drift toward the center. Stars interact in chaotic, close-packed orbits, occasionally getting too close and being torn apart. Even the galaxy as a whole contributes by stirring matter through rotational motion. The central black hole becomes a focal point for this activity, gradually accumulating more and more mass simply because everything around it is constantly in motion. What makes this difference even more striking is that supermassive black holes do not have to work any harder than their tiny cousins. They do not need stronger instincts or better strategies. They do not move around hunting for meals. They just exist in the right place, and the environment does the rest. Everything is delivered to them by the gravitational currents that naturally occur in dense galactic regions. It is the universe's most extreme demonstration of the phrase, "location is everything." There is also something deeply ironic about how cleanly the environment determines long-term growth. The black holes that eventually become supermassive do not start out any more impressive than the smaller ones. They are born from collapsing stars or merging stellar remnants, just like typical black holes. But what happens next, the trajectory of their entire existence, depends entirely on what the galaxy decides to offer them. If they find themselves surrounded by rich deposits of matter, they have the potential to grow into cosmic queens and kings. If they form in quiet regions, they remain unnoticed, forever small and underfed. Over cosmic time, this environmental advantage compounds dramatically. A black hole that experiences even moderate feeding early in its life gains mass more quickly, which increases its gravitational influence. This lets it gather material from slightly farther away, which in turn increases its mass again. The growth becomes exponential in the long run. That is how a black hole in the center of a galaxy can balloon to millions of solar masses, while its quiet cousins barely change after their initial formation. Even interactions within the galaxy play a major role. Gas clouds may be nudged inward by passing stars. Stellar winds from clusters can push material toward the heart of the galaxy. Galactic bars, long, stretched-out structures of stars, can channel matter into the central region like a gravitational conveyor belt. Every one of these processes enriches the environment around the central black hole, ensuring a continuous flow of cosmic nourishment. Meanwhile, a black hole on the galaxy's outskirts might spend the same amount of time drifting through empty space, like a wanderer who keeps checking the fridge, even though they know nothing is inside. Another factor is mergers between galaxies. When two galaxies collide and eventually combine, their central regions rush together in a chaotic swirl of gas, dust, and stars. This sudden upheaval can produce a spectacular feeding event for the central black holes. The inflow of fresh material triggers a growth spurt that can transform a previously modest black hole into a cosmic titan. After the merger, the resulting galaxy often carries a single, much larger black hole at its core, one that may shine or feed for millions of years after the chaos settles. Ultimately, the divide between tiny black holes and supermassive giants is not a story of ambition or effort. It is a story of opportunity. The universe provides each black hole with a unique set of surroundings, and those surroundings do all the heavy lifting. Some black holes end up in quiet corners with barely anything to pull in. Others are placed at the energetic crossroads of galactic activity, where matter flows freely and growth is all but guaranteed. In the end, the universe shapes their diet, their size, and their destiny, not through intention, but through the quiet, persistent logic of cosmic geography. When galaxies collide, the universe throws a party that has no respect for personal space. Stars swing past each other in near misses, Gas clouds slam together like cosmic traffic accidents, and gravitational tides stretch each galaxy until they look like abstract art painted by a frustrated giant. In these chaotic, over-the-top moments, black holes suddenly find themselves in the middle of the greatest dining opportunity they will ever experience. If the typical feeding routine of a black hole is like waiting patiently for crumbs to drift in, a galactic collision is the moment someone kicks the entire buffet table over and all the food comes sliding toward you at once. To understand why this happens, imagine two galaxies approaching each other over millions of years. From a cosmic distance, it looks graceful, like two spirals dancing. But zoom in, and the choreography becomes something much messier. Each galaxy contains vast reservoirs of gas, great swirling clouds that usually mind their own business. But when the galaxies draw near, their mutual gravity begins tugging everything out of alignment. Gas clouds start drifting, stretching, and colliding with one another. It is like a cosmic mosh pit, where no one asked for a mosh pit. This violent rearrangement of material does one crucial thing. It funnels gas toward the centers of the merging galaxies. Gravity acts like a sculptor, shaping tidal forces that nudge, pull, and finally push enormous amounts of gas into narrow channels that spiral inward. What was once a peaceful distribution of material becomes a set of rivers, all flowing straight toward the galactic cores. And waiting in those cores are black holes that have been quietly, politely minding their own business for eons. Suddenly, the rules of the game change, Instead of scraping by on thin streams of matter or the occasional unlucky star, these central black holes are handed an all-you-can-eat invitation. The inflowing gas compresses as it travels inward, accelerating under the pull of gravity and heating up as particles slam into each other. By the time this gas reaches the inner region of the galaxy, it is moving fast, glowing brightly, and ready to become the raw material for explosive black hole growth. This moment is often the turning point for black holes that eventually become supermassive. Before the collision, they may have been comfortable and well-fed, but nothing extraordinary. After the collision, they begin gaining mass at rates that would make their previous growth look like a diet. The influx of gas forms an enormous, turbulent accretion disk that glows with more intensity than anything the galaxy has produced before. The black hole's gravitational pull deepens with every bite, making the inflow even more efficient. It is the cosmic equivalent of giving a hungry teenager unlimited pizza after a long day of sprinting. The plate is going to be empty in seconds, and the refrigerator is going to fear for its life. What makes galactic collisions even more dramatic is that they rarely happen in isolation. When galaxies collide, their stars usually pass right by each other without direct impact. Space is, after all, mostly empty, but their gas clouds do not share that courtesy. Gas is messy. It compresses, heats, and swirls into new shapes. These collisions generate shock waves that travel through the galactic environment, pushing even more material toward the center. This means the black hole gets not just one influx of gas, but a series of escalating waves, each one dumping more fuel into the feeding zone. The result is a feeding frenzy so intense that it can transform the black hole from a quiet presence into a quasar, a blazing beacon visible across billions of light years. During these periods, the black hole's accretion disk becomes astonishingly luminous, shining brighter than everything else in the merging galaxies combined. The black hole itself is still as invisible as ever, but its chaotic dinner plate becomes a spotlight announcing to the universe, "Yes, I am eating extremely well, thank you." In some cases, there are two black holes involved, one from each galaxy. At first, they orbit one another, dancing in the disturbed center like two heavyweight fighters circling before the main event. As gas flows inward and stars scatter away, the two black holes spiral closer and closer together. Eventually, they may merge into a single, larger black hole, unleashing powerful ripples through space-time, and once they combine, the resulting black hole often finds itself surrounded by even more material from the continuing collision, leading to yet another surge of growth. It is a cosmic growth spurt layered on top of another growth spurt, the kind of thing only the universe could stage without accidentally burning down the room. The environment after a collision remains chaotic for a long time. Streams of gas continue pouring inward. Star formation rates skyrocket as compressed clouds collapse into new stars. But many of these stars will eventually wander too close to the turbulent gravitational center and be devoured as well. Everything becomes part of a feedback cycle that overwhelmingly favors black hole growth. A peaceful galaxy can go billions of years without offering its central black hole much to chew on. But a merging galaxy can fatten that same black hole in a fraction of the time. Perhaps the most astonishing part is that these collisions are not rare accidents. The universe is full of galaxies on slow-motion collision courses. Many large galaxies have experienced multiple mergers throughout their history, each one providing another round of abundant material for black holes to feast on. The black holes that sit at the centers of modern galaxies are shaped not only by their own gravitational pull, but by the grand cosmic dramas that have played out around them over billions of years. In the end, galactic collisions are the universe's most spectacular dining events. They take quiet, stable galaxies and churn them into chaotic feasts. They bring black holes everything they could ever want in terms of fuel, and then some. And through this process, they turn modest black holes into cosmic giants, gorgeously luminous, endlessly growing and forever shaped by the chaos that once swept through their galactic homes. If black holes ever wrote a cookbook, the first chapter would probably be titled, "Patience, the Only Ingredient You Really Need." For all their dramatic power and gravitational flair, black holes are, at their core, creatures of astonishing stillness. They do not chase, they do not hunt, and they certainly do not go searching for snacks. They wait, sometimes for millions of years, sometimes for longer than entire species survive on planets. In a universe that loves explosive events and flashy transformations, black holes are the ultimate slow-cooking chefs, simmering quietly in the dark and biding their time until the next meal drifts close enough to fall in. What makes this patience so uncanny is that everything else in space is in constant motion. Stars burn frantically, galaxies swirl, gas clouds billow and collapse into new shapes, and planets race around their suns like clockwork runners. But a black hole sits at the center of all this motion like a cosmic monk who has decided that enlightenment will arrive eventually. So why not sit still and let the universe come to them? Their power does not come from activity, it comes from inevitability. Given enough time, something will wander near. Something always does. And the black hole, with infinite composure, will be there when it happens. This waiting game begins the moment a black hole settles into its environment. Unlike stars, which create their own energy, black holes rely entirely on what the universe provides. If a region of space is rich with material, a black hole may enjoy consistent feeding. But if the surroundings are empty, the black hole simply enters a long, silent phase of anticipation. This can last for millions, tens of millions, or even billions of years. In human terms, it would be like waiting from the Stone Age to the present day for a single bite of food, and not complaining once. During these vast, empty stretches of time, a black hole does not weaken or fade. It does not get hungry in any biological sense because hunger requires metabolism, and black holes operate on nothing resembling metabolism. They do not burn energy, they keep it. They do not starve, they remain exactly what they are, as if the concept of malnutrition simply does not apply. The universe designed them to be perfect observers, and their patience is built into the very laws of physics that define them. What sets this patience apart from any biological comparison is the scale of time involved. A black hole may sit in a quiet patch of space for longer than continents have existed on Earth, watching the galaxy slowly rotate, waiting for the gravitational currents to shift just enough to bring new material within reach. And when that moment finally arrives, when a drifting cloud or an unwitting star passes a little too close, the black hole responds instantly. A predator frozen in time until the moment the prey steps directly onto its tongue. But these meals, rare as they might be, can be spectacular. A black hole that has waited for millions of years can suddenly light up with activity when new matter enters its domain. The infalling material heats, glows, and spirals inward, transforming the once dark region into a dazzling display of energy. For a brief time, the black hole becomes busy. Cosmically speaking, of course, it is still not moving, but everything around it is, swirling frantically as the accumulated matter releases its final bursts of light. Then, as quickly as it began, the feast ends, the glow fades, and the black hole returns to stillness. What makes this rhythm so intriguing is how different it is from the universe's usual pace. Stars have lifespans governed by how fast they burn fuel. Galaxies evolve through constant motion. Even planets experience seasonal changes. But black holes live in a different kind of time. They do not rush, they do not decay by waiting, and they do not measure existence in cycles of activity. They simply persist, wholly unbothered by how long it takes for the next opportunity to fall their way. This endless patience also shapes their surroundings in subtle ways. A black hole that waits long enough becomes the quiet center of gravitational rearrangement. Slowly, very slowly, matter that was once scattered across vast distances drifts, shifts, and settles into new patterns influenced by the black hole's gentle tug. Over eons, this can lead to a quiet accumulation, a gradual gathering of potential meals. While the black hole waits, the universe itself does the prepping. Gas clouds merge, dust thickens, orbits decay, and eventually the ingredients begin sliding closer. The black hole simply remains present, letting the cosmic slow cooker do its work. Even when the universe is in no hurry, black holes do not grow restless. They are timeless by design, with no sense of urgency. If a star does not pass near them today, maybe it will in a few 100 million years. If a gas cloud drifts away instead of inward, there will always be another one forming somewhere. This calm, almost meditative patience is one of their most striking qualities. Black holes grow not through effort, but through the quiet confidence that time is on their side. And indeed, time is always on their side. Over the lifetime of a galaxy, countless small opportunities arise. A wandering star, a disrupted gas cloud, a stray fragment of debris. Each becomes a tiny addition to the black hole's mass. Not dramatic, not urgent, but inevitable. Each small meal strengthens the gravitational pull, and each strengthened pull increases the chance of another encounter millions of years later. It is a long game, the longest of long games, and black holes have mastered it. So while their growth may come in sudden bursts during cosmic upheavals, the truth is that most of a black hole's existence is spent waiting, silent, motionless, patient beyond human imagining. If the universe is a vast kitchen, black holes are the quiet chefs who trust that the ingredients will arrive eventually, and when they do, the slow cooking process will transform them into something greater. They remind us that in the grandest stretches of time, patience is not just a virtue, it is a cosmic strategy. If black holes had a workout routine, it would consist entirely of spinning, not running, not lifting, not stretching, just pure, relentless rotation that gets faster the more they consume. It is one of the strangest, most unintuitive features of these cosmic enigmas. When a black hole eats, it does not just get heavier. It also gets better at twirling, and as its spin accelerates, an entirely new set of rules takes over, subtly reshaping what kinds of matter it can pull in, how that matter behaves near the event horizon, and even how efficiently the black hole can devour its cosmic meals. By the time a black hole has reached maturity, its spin is not just a detail, it is a defining personality trait. To understand how this happens, we have to imagine what it means for something to spin when that something has no solid surface. Black holes are regions of warped spacetime, not physical objects, yet they can rotate with astonishing intensity, carrying angular momentum the way a figure skater carries grace, except with far more terrifying consequences. When matter spirals inward toward a black hole, it almost never falls straight down. Instead, it arrives with some sideways motion. Gas, dust, and even stars tend to orbit slightly as they approach, and this orbital motion transfers angular momentum to the black hole. Every particle that drops in gives the black hole a microscopic push. Over millions of years, these pushes add up, until the black hole is spinning so rapidly that even space-time itself begins to twist around it like a cosmic whirlpool. This twisting effect, known as frame dragging, becomes stronger as the spin increases. Near a rapidly spinning black hole, space-time is dragged around at such high speeds that anything entering the region is forced to rotate as well. The black hole is no longer just pulling inward, it is stirring. It is as if the black hole has become a cosmic mixer, and any matter approaching its edge gets caught in the swirl, whether it likes it or not. This enforced rotation changes the rules of eating in dramatic ways. For one thing, spin changes how close matter can get before falling in. A non-spinning black hole allows matter to orbit at a certain minimum distance, but a rapidly spinning one lets material orbit closer without being swallowed. That might sound counterintuitive, being allowed closer before falling in, but it means the black hole is effectively reaching farther with gravitational influence, even as it keeps the door shut until the very last moment. This allows the black hole to extract more energy from the matter spiraling inward. A spinning black hole can feed more efficiently, turning infalling material into heat, light, and motion far better than a non-spinning one. It becomes a more skillful eater, transforming the energy of its food into powerful radiation emitted from its disks. Spin also changes what directions matter can safely approach from. Approaching a spinning black hole from the direction of the spin, called the prograde direction, makes it easier for matter to slip inward because the rotation helps pull it in. Approaching from the opposite direction, the retrograde direction, is like trying to walk the wrong way on a cosmic moving walkway. The spin creates resistance, making it harder for matter to fall in. Some material approaching from the retrograde direction even ends up being deflected away, like a rejected appetizer. The black hole, in effect, becomes choosy. Its spinning motion shapes a preference about the angles and directions from which matter can successfully join its mass. This behavior starts to resemble something eerily close to adaptation. Not adaptation in a biological sense, black holes do not think or strategize, but a process where incoming material changes the black hole's internal conditions, and those conditions then alter how the black hole interacts with future material. Growth changes spin, spin changes diet. Diet changes future growth. The loop resembles natural selection, except without any intention, competition, or life. It is simply physics being dramatic. A rapidly spinning black hole also creates a region just outside its event horizon called the ergosphere, a distorted zone where no object can remain still because space-time is being dragged around too violently. In this region, matter behaves differently. It can gain or lose energy in unusual ways. Some processes can even extract energy from the black hole's spin itself, slowing it slightly while powering jets or radiation. So the spin becomes not just a consequence of what the black hole eats, but a resource that can be drained by the interactions with surrounding material. It is as if the black hole has developed an internal energy reserve that the environment can tap into under the right circumstances. Interestingly, black holes cannot spin infinitely fast. There is a theoretical upper limit, a maximum twirl the universe allows before physics starts whispering, "Okay, calm down." Some black holes approach this upper limit, spinning so rapidly that if they had edges or surfaces, those surfaces would be traveling at nearly the speed of light. When they reach this point, their behavior becomes extremely efficient. Infalling matter releases enormous amounts of energy, and the black hole itself becomes a highly organized gravitational machine. If black holes were machines built by engineers, these maximally spinning ones would be the sleek, optimized models, the kind that run quietly, operate flawlessly, and cost more than anyone should reasonably pay. Another astonishing consequence of spin is its feedback on the surrounding environment. A fast-spinning black hole can influence the shape of the surrounding accretion disk. It can tilt the disk, twist it, and even break it into separate rings under extreme conditions. This reshaping creates different pathways for incoming matter, altering what gets eaten now versus what gets stored in the swirling outskirts. Over time, this can dramatically change how the black hole grows. Two black holes with the same mass but different spins can end up evolving in completely different ways, simply because one inherited more rotational energy from its past meals. All of this leads to the surprising conclusion that black holes are not static. They are not final. They evolve not only in size, but in behavior. Their spinning shapes their future, alters their environment, and modifies how they interact with the universe. They are not alive, but they share the signature of living things, change driven by experience. Every meal leaves a mark. Every encounter adjusts the next. In the silent, swirling ballet of space-time, black holes become not just destinations of matter, but dynamic, ever-shifting creatures, shaped by the very cosmos they consume. Black holes have a reputation for being the universe's tidiest diners. The popular image is simple. Matter goes in, nothing comes out, and everything is neatly hidden behind the event horizon like a cosmic magician who refuses to reveal the trick. But this image is only half the truth. In reality, many black holes are surprisingly messy eaters. They do not merely swallow matter. They sometimes slingshot enormous jets of energy and particles out into space at mind-boggling speeds. These jets can stretch across thousands of light years, carving neon streaks through the darkness. It is the gravitational equivalent of someone taking a big bite of a sandwich and accidentally spraying crumbs all the way to the back wall. The origin of these jets is not inside the black hole. Nothing escapes from within the event horizon, but in the wild, chaotic regions just outside it. When matter spirals inward, it enters a zone where conditions become almost unimaginably extreme. The gas becomes superheated and ionized, magnetic fields twist into tangled knots, and particles whip around at speeds approaching that of light. In this electrically charged frenzy, the black hole's immediate surroundings become a cosmic pressure cooker. And something extraordinary begins to happen. The swirling magnetic fields start acting like rails, accelerating some of the particles upward and outward instead of allowing them to fall in. This process begins with a strange property of the material swirling around the black hole. It is not all destined to fall inward. Some of it, especially the charged particles caught in magnetic loops, gets redirected. The magnetic fields grow stronger and more organized as the matter spirals closer, amplifying themselves like a microphone feedback loop turned way past reasonable volume. These magnetic fields twist upward along the black hole's poles, forming narrow funnels. Within these funnels, charged particles are whipped into tight beams and launched outward with incredible force. The black hole, in a moment that seems to defy its own gravitational personality, spits out a pair of precisely aimed cosmic fire hoses. These jets are not polite little streams either. They are among the most energetic structures in the universe. Some jets blast matter outward at more than 99% of the speed of light. At those speeds, the particles approach the upper limit that physics will allow. The jets also glow intensely, emitting radiation across the electromagnetic spectrum, from radio waves to X-rays, turning them into beacons that astronomers can spot halfway across the universe. If black holes are the ultimate minimalists, then jets are the accidental neon signs they never intended to flip on. Even more surprising is how structured these jets can be. For something born out of chaos, they often emerge astonishingly straight, like laser pointers maintained with the precision of a cosmic engineer. The magnetic fields collimate the flow of particles, squeezing it inward so the jet does not spread sideways prematurely. This is why the jets can travel uninterrupted over unbelievable distances, punching through the surrounding clouds, star-forming regions, and even whole swaths of the galaxy. The launching of jets also depends heavily on the rotation of the black hole. A rapidly spinning black hole drags space-time around with it in a whirl, twisting magnetic fields even more tightly. This twisting acts like a motor that pumps energy into the jets. The black hole, despite swallowing matter with silent authority, ends up supplying power indirectly through its spin. It is like using the momentum of your own spinning chair to launch a paper airplane straight across the room, but scaled up to astrophysical proportions. As a result, some of the brightest jets come from the fastest spinning black holes, which turn their polar regions into portals of raw, focused energy. But the jets do not just shoot outward and disappear. They have consequences, dramatic ones. A powerful jet can heat and compress gas in the surrounding galaxy, changing how stars form in the regions it passes through. It can carve cavities in interstellar clouds, stir up turbulence, and even regulate the temperature of galaxy clusters. In a strange twist of cosmic irony, a black hole's jets can help determine the fate of galaxies millions of times larger than the black hole itself. A messy eater, yes, but a messy eater whose crumbs reshape entire cosmic landscapes. The bizarre part of the story is that jets represent a delicate balance of forces. Too much material flowing inward, and the magnetic fields may get overwhelmed, choking off the jet. too little material, and there is nothing to accelerate. Jets flourish only when the environment produces just the right blend of magnetic stability, rotational energy, and inflowing matter. They are rare, temperamental, and extraordinarily fussy, like cosmic fountains that activate only when the physics surrounding the black hole hits a very specific combination. And the direction of the jets is no accident. They always launch from the poles of the black hole because that is where the magnetic fields can funnel the particles without interference from the chaotic swirling disk. The swirling material around the black hole might be a maelstrom, but the poles become escape routes, narrow corridors where particles can slip through the gravitational storm and shoot outward into the calm of interstellar space. In their own way, jets reveal something profoundly contradictory about black holes. These cosmic giants, known for swallowing everything in their path, are also capable of unleashing some of the most energetic outflows in existence. They are creatures of consumption, yet they produce outward blasts stronger than anything a star can manage. They are perfectly silent, yet they create structures visible across cosmic time. And while they are famously private, hiding everything that passes their boundary, they simultaneously broadcast their presence with jets that scream their existence into the cosmos. When black holes devour matter, they do not always do it neatly. Their magnetic fields snatch up particles, aim them with frightening precision, and fire them off into eternity. In that sense, black holes are cosmic diners with terrible table manners, creatures that eat with such enthusiasm that the universe ends up wearing half the meal. If you picture a galaxy as a bustling cosmic city, stars as streetlights, gas clouds as neighborhoods under construction, and dark matter as the zoning laws no one sees, then the central black hole is the overly involved authority figure who insists everything run on schedule. It does not raise its voice, it does not pace the hallways, and it certainly does not patrol the galaxy with binoculars. Yet somehow, through a mixture of gravitational influence and raw, energetic outbursts, it manages to regulate the entire community around it. It decides when new stars get to form, when certain regions stay quiet, and when the galactic lights dim for the cosmic equivalent of curfew. And the galaxy, amazingly, listens. At first glance, this seems impossible. How could something that occupies a tiny fraction of a galaxy's volume shape the behavior of structures millions of times larger than itself? The answer lies in the black hole's ability to influence the galaxy without moving an inch. It does not need to chase anything. Its gravity, combined with the energy produced by the surrounding matter, is enough to sculpt the galaxy's evolution. This influence is subtle in quiet galaxies and dramatic in active ones. Either way, the central black hole becomes what scientists call a regulator, though strict but fair parent is probably closer to the truth. One of the most important tools black holes use in this role is energy. When material spirals into the accretion disk and heats up, it produces radiation, heat, and sometimes powerful winds. These energetic outflows propagate outward through the galaxy, pushing against surrounding gas. Imagine a giant cosmic hand smoothing wrinkles out of a blanket, except the blanket is made of cold hydrogen, and the hand is made of light, heat, and shock waves. this push has real consequences. Gas clouds, the raw ingredients for star formation, can be compressed, heated, or scattered depending on how strong the outflow is. A gentle push might nudge a cloud into forming new stars. A strong push might rip the cloud apart, halting star formation entirely. It is this delicate balance that gives black holes their parental aura. If too many stars are forming too quickly, the black hole steps in with energetic winds that blow gas outward, cooling down the galactic frenzy. If star formation slows too much, the black hole quiets down, allowing gas to settle and condense again. Over millions of years, this push and release cycle regulates how new stars emerge, preventing the galaxy from burning through its fuel too quickly. It is cosmic budgeting, ensuring the galaxy does not spend all its gas in one reckless spree of star formation and end up dim, cold, and empty. Some galaxies demonstrate this influence particularly dramatically. When the black hole becomes exceptionally active, usually because it is feeding aggressively, the central region can erupt with so much energy that enormous bubbles of hot gas expand outward, carving cavities in the galaxy's structure. These bubbles can shut down star formation across vast areas, essentially telling the galaxy, "Okay, everyone calm down, no more building projects for a while." Galaxies that undergo these events often show signs of suppressed star formation for millions of years afterward, and all because their central black hole had one enthusiastic dinner too many. But the influence does not stop with energy bursts. The very gravity of the black hole can shape the orbits of stars near the galactic center. These stars move in tight, eccentric paths, their motions determined by the black hole's mass. In some galaxies, the central regions become dense, swirling hubs where stars whip around like dancers, following an invisible metronome set to dangerously fast. This gravitational choreography stabilizes the inner galaxy, preventing large-scale collapse and helping maintain the structure of the central bulge. Without this gravitational anchor, the galaxy might warp into more chaotic shapes over time. The black hole also affects how gas flows through the galaxy. Many galaxies contain streams of gas slowly drifting inward toward the center. The black hole acts as a drain for this flow, but a very selective one. When it is active, its surrounding energy heats the gas and pushes it outward, slowing the inflow. When it is quiet, the gas can sink inward more easily. This creates a self-regulating cycle. Too much inflow leads to too much activity, which then suppresses the inflow. Too little inflow quiets the black hole, allowing the next wave to arrive. It is an elegant equilibrium that keeps the galaxy from devolving into extremes. But perhaps the most charmingly absurd aspect of this influence is the scale mismatch. The black hole might be millions of times the mass of the Sun, but the galaxy around it is often trillions of times more massive. Yet the black hole's outbursts can heat and move material across distances so vast that light itself takes tens of thousands of years to cross them. If a black hole sends out a wave of energy today, the outer galaxy may not feel the effects until long after entire civilizations on distant planets have risen, fallen, and been forgotten by time. Cosmic parenting is nothing if not slow-paced. This regulation of star formation explains why galaxies that host actively feeding black holes often appear strangely calm or even underpopulated with new stars. Energy from the central region prevents cold gas from settling into dense clouds, effectively keeping the lights dim and stopping the stellar equivalent of a neighborhood baby boom. In other galaxies where the black hole sleeps quietly for eons, star formation can flourish, filling the galaxy with bright, young stars in sprawling spiral arms. What makes all of this so astonishing is the complete lack of intention behind it. The black hole is not trying to maintain order, preserve resources, or shape the future of the galaxy. It is simply responding to the physics of its surroundings. Yet the result looks uncannily like oversight. The galaxy grows, evolves, quiets, and reignites in cycles, all subtly influenced by this compact gravitational overseer at its center. In the end, a galaxy is not simply a collection of stars drifting through space. It is a system shaped in part by the moods of its central black hole. With each burst of energy, each gravitational tug, each wave of heat, the black hole guides the galaxy's evolution with the quiet authority of someone who always knows when it is time to turn out the lights and tell the stars to settle down for the night. If black holes had a relationship status, its complicated would barely scratch the surface. Because when two of them meet, they do not simply hang out, exchange pleasantries, and go their separate ways. They begin an elaborate, unavoidable dance that ends in one of the most dramatic events the universe can produce: a merger. It is as if two heavyweight champions step into a ring, circle each other for ages, and then finally collide in a moment so intense it sends tremors rippling through the very fabric of reality. When black holes merge, space-time does not just react. It sings, it shivers, and it broadcasts the event to the universe in the form of gravitational waves. These mergers begin quietly, often in the aftermath of galactic chaos. When galaxies collide, or when dense stellar environments jostle their inhabitants like marbles in a shaken jar, black holes may find themselves drifting closer to one another. At first, nothing noticeable happens. They pass one another like strangers on a very dark street. But gravity has a way of turning passing encounters into long-term commitments. Each black hole pulls on the other, subtly slowing their paths and nudging them into a mutual orbit. It is not a fast process. Black holes can spend millions of years tracing spirals around each other, tightening their orbit millimeter by millimeter, the cosmic equivalent of a slow-burn friendship that eventually becomes inseparable. During this long courtship, the two black holes begin to interact with the surrounding space in eerie ways. Their combined gravitational pull distorts the orbits of nearby stars. Gas clouds feel the tug of their joint influence and may spiral inward, heating and glowing as they encircle the soon-to-be couple. These environmental shifts create a zone of turbulence around the orbiting pair, like the whirlpool that forms when two ocean currents meet. But the most spectacular changes occur in the space-time between the black holes themselves. As they orbit, the black holes cause space-time to ripple outward in waves, gravitational waves, that carry energy away from the system. These waves are not like light or sound. They are distortions of the very geometry of existence, stretching and squeezing everything they pass through. With each wave launched into the universe, the black holes lose a tiny bit of orbital energy. And because they lose energy, they spiral closer. And because they spiral closer, the waves grow stronger. It is a feedback cycle that ends in a crescendo, building toward a moment of cosmic drama. The final seconds before a merger are some of the most violent in the universe. The two black holes whip around each other at speeds approaching that of light. Their event horizons blur, distort, and stretch as gravity intensifies. Imagining this scene requires abandoning intuition entirely. Two invisible spheres of warped space-time twist together in a gravitational dance so extreme that the equations describing it only settled down when scientists developed numerical methods powerful enough to simulate them. For all of human history, no one had seen or detected such an event until recently, when the ripples from distant mergers finally reached Earth. Tiny tremors that moved our detectors by less than the width of a proton, yet carried the signature of cosmic giants combining. And then comes the moment itself, the collision. It is silent because sound does not travel in space. It is dark because black holes emit no light. Yet it is astonishingly energetic. When the event horizons fuse, a burst of gravitational waves radiates outward, carrying away a staggering amount of energy. The newly formed black hole settles into place, wobbling for a moment like a massive bell that has been struck before becoming smooth and stable again. The universe takes note of the new arrival, a larger, heavier creature formed from the union of two smaller ones. What makes these mergers particularly extraordinary is that they produce something brand new. The resulting black hole is not merely the sum of its parents' masses. In fact, some of the mass is converted directly into gravitational wave energy during the merger, a process Einstein predicted long before anyone had the tools to detect it. The final black hole ends up slightly lighter than the total of its predecessors, but it carries their combined gravitational legacy: more mass, more pull, and often more spin. It is a transformed being, shaped by the violent union that created it. The aftermath of a merger can reshape entire regions of space. If the new black hole receives a recoil kick from the way the gravitational waves were emitted, something that depends on its spin and the orientation of the merger, it can actually begin moving through the galaxy at surprising speeds. Some merged black holes may drift away from the galactic center entirely, wandering like exiled monarchs carrying the merged memories of their past selves. Others settle back into the heart of their galaxy, becoming the gravitational anchor that organizes the stars around them. These mergers also play an enormous role in shaping the population of black holes in the universe. A black hole that merges early in cosmic history may go on to merge again later, growing through repeated collisions like a snowball rolling down a cosmic hill. By the time billions of years have passed, these merger chains can produce colossal black holes far larger than any single star could create. In this way, the universe builds its giants, not quickly, but through a series of dramatic unions that each send space-time trembling. What makes black hole mergers so captivating is the way they challenge our expectations. Two objects known solely for swallowing everything in their reach end up producing one of the most expressive cosmic signals ever discovered. They do not simply combine, they announce themselves with waves that expand across the universe for billions of years. They are creatures of pure gravity, yet their collisions create echoes that we can measure here on Earth, a tiny planet orbiting an ordinary star. In the end, a black hole merger is not just a combination of mass. It is a moment where the universe reveals one of its most powerful truths. Even its darkest objects can create disturbances that reach across time and space, telling the story of two cosmic beasts becoming one and leaving behind a deeper, heavier, more enigmatic creature than either of them could have been alone. Studying black holes is a bit like trying to film a documentary about a creature that refuses to come out of its cave, never leaves footprints, and does not reflect light. Scientists who take on this challenge become cosmic wildlife observers, crouched behind metaphorical bushes, holding extremely sensitive instruments instead of binoculars, trying to piece together the behavior of an animal that actively erases the evidence of its existence. The universe does not make this easy. Black holes hide behind a curtain of warped space-time, revealing nothing directly. Yet paradoxically, they produce some of the loudest signals nature can offer, signals that allow scientists to reconstruct their growth, their habits, and their cosmic history. The first clue comes from light, even though the black hole itself emits none. Everything around a black hole becomes a luminous storyteller. The swirling matter in the accretion disk radiates intensely as it heats, brightens, and eventually vanishes past the point of no return. This light is not random. It has structure, patterns, and rhythms. By studying the wavelengths of this radiation, its brightness, its flickers, its sudden flares, scientists can deduce what the black hole is doing. It is a bit like inferring that a hidden animal is eating because you can hear the crunching of leaves. The black hole stays invisible, but the light from the surrounding chaos becomes a beacon of activity. Some of this light travels across unimaginably vast distances, carrying signatures of the disk's temperature and turbulence. When the disk is hot and thick, the radiation peaks at high energy wavelengths. When it is thinner and cooler, the light stretches into lower energy bands. In this way, astronomers can determine not just whether a black hole is feeding, but how fast. A bright, flickering glow suggests active growth. A dim, steady band suggests a period of quiet waiting. These variations allow researchers to track the black hole's dietary cycles, even though the eater itself remains hidden behind a curtain of darkness. But light is only one part of the story. The universe also offers scientists a different kind of messenger, ripples in spacetime known as gravitational waves. These waves behave like vibrations on an enormous trampoline stretched across the cosmos. When black holes collide or spiral around one another, they send waves outward in all directions, stretching and compressing space-time with every passing moment. These waves travel across billions of light years, arriving at Earth so faint that detecting them requires instruments capable of measuring changes smaller than the width of an atomic nucleus. Yet the information they carry is profound. Gravitational waves reveal details that light cannot. They carry the signature of black hole masses, their spins, their orbits, and the moment they merge. When scientists record these waves, they are essentially listening to the universe's deepest bass notes. Each merger creates a unique tone, a pattern of rising frequency and intensity that scientists call a chirp. By analyzing these chirps, researchers can determine how large the black holes were, how fast they were moving, and how much mass transformed into pure gravitational wave energy during the collision. It is as if the black holes announce their final act with a roar loud enough to travel across cosmic distances, even though no sound is involved. Once the chirp ends, the newly merged black hole emits a faint, fading oscillation, a ringing pattern that slowly dies down. This ringing carries details about the newborn black hole's size and spin, much like listening to the resonance of a struck bell reveals its shape. Scientists use these signatures to confirm the identity of the final black hole that emerges from the merger. In this way, gravitational waves act as both the soundtrack and the biography of the black hole's evolution. The combination of light-based observations and gravitational wave detections gives astronomers a toolkit unlike anything available to previous generations. Telescopes can track the glow of matter as it spirals inward. Radio arrays can detect jets shooting into interstellar space. Space-based detectors can hear the faint tremors of distant collisions. Each method catches the black hole performing a different behavior, and together they build a holistic picture of these invisible giants. Scientists become cosmic field researchers, piecing together behavioral patterns from traces left behind by forces that should be silent and invisible. One challenge in this observational pursuit is that black holes often exist in environments crowded with distractions. Gas clouds, bright stars, magnetic fields, and dust lanes can contaminate or distort the signals. To solve this, scientists build models, complex simulations that recreate accretion disks, turbulence, and gravitational interactions. They compare these models to real data, adjusting parameters until the simulation behaves the way the universe behaves. It becomes a kind of celestial detective work. If the observed light flickers in a certain way, what shape must the accretion disk be? If gravitational waves show a specific pattern of increasing frequency, what were the masses of the black holes involved? Each answer uncovers another layer of the creature's hidden life. The most ambitious efforts involve imaging the environment directly around the event horizon, using networks of radio telescopes spread across Earth. By synchronizing these telescopes into a single planet-sized observatory, scientists have captured silhouettes of black holes, dark circles framed by glowing rings of hot plasma. These images are not portraits of the black hole itself, but of the desperate light trying and failing to escape. It is the closest we have ever come to seeing the unseeable. Studying black holes requires creativity, technology, and a willingness to accept that the subject of the study will never appear directly. Everything scientists learn comes from interpretation, from observing how black holes disrupt their surroundings. It is the science of shadows and echoes, of ripples and footprints. Yet from these faint traces, an entire field of knowledge rises, one that continues to reveal the hidden habits of cosmic giants that would prefer, quite stubbornly, to remain unseen. And despite their secrecy, black holes cannot help leaving trails. Their meals flare with light, their collisions shake space-time. Their presence bends the paths of stars. From these subtle and not so subtle disturbances, scientists reconstruct their stories, one ripple, one photon, one cosmic clue at a time. If you could fast forward the universe like a cosmic time lapse, the first thing you would notice is how quickly everything bright and lively begins to fade. Stars burn through their fuel and wink out. Galaxies drift apart like old friends who once shared everything but now barely exchange glances. Even the dramatic events, explosions, collisions, births of new stars, become rare, then rare again, until the universe settles into a quiet that feels almost like it has run out of stories to tell. And yet, in that silence, one kind of object continues to change, to influence, and to evolve long after everything else has given up on the concept of activity: black holes. To imagine their future, you must picture an era when galaxies no longer collide the way they once did, when star formation has stopped, and when the universe has stretched itself so wide that light takes longer than the human imagination can handle to cross even small regions of space. Gravity grows lonely, heat grows scarce. Time stretches into epochs that make even the age of the current universe seem like a brief, energetic opening act. In this slow twilight of cosmic history, black holes remain among the few things still capable of doing anything noticeable at all. Their endurance comes from their very nature. Black holes do not rely on fuel. They do not need fusion or temperature or stable surroundings. They simply exist, warping space-time and waiting for whatever minuscule bits of matter are still drifting around. Even when stars are gone, black holes still have access to stray particles, dark matter clumps that happen to pass by, and the thin haze of gas that remains from ancient cosmic processes. Over ridiculous stretches of time, they can absorb these leftovers, continuing their slow, patient growth while everything else lies dormant. They become the universe's last gravitational gardeners, sweeping up anything that has not already been claimed. In the far future, so distant that trying to express the number of years involved becomes an exercise in futility, whole galaxies will be held together less by their shining stars and more by the gravitational anchors of their central black holes. As stars fade into cold remnants, some will drift inward after billions of years, eventually falling into the central black hole and giving it one final tiny boost of mass. These late meals will be infrequent, but in a universe that refuses to rush, even the occasional bite carries significance. Each small addition keeps the black hole active in its own quiet way, giving it something to do while the rest of existence embraces retirement. Meanwhile, smaller black holes, those created by individual stars, will persist like wanderers in a cosmic desert. Their surroundings will grow so empty that encounters with matter become rarer than cosmic miracles. But even then, they remain capable of growth whenever chance allows. A lonely neutron star drifting too close, a rogue planet still intact from ancient times, a faint scattering of gas, all of it can still be claimed. In a universe where almost nothing else is still interacting, black holes become the final dynamic participants, but their fate is not to eat forever. There comes a point in the deep, deep future when even black holes must face a slow, inevitable transformation. As the universe continues expanding and cooling, a faint and almost ghost-like process begins to matter: Hawking radiation. This radiation, predicted by quantum theory, allows black holes to slowly lose mass over incomprehensible spans of time. It is like an incredibly slow leak, one drop every eternity, gradually reducing the black hole's size. For most of cosmic history, this effect is laughably tiny, utterly drowned out by the matter they consume. But in the farthest reaches of time, when meals have become a myth and the universe itself is colder than any star ever was, Hawking radiation becomes the only game left to play. Large black holes, the giants at the centers of galaxies, will take unimaginably long to evaporate. If the human brain tries to imagine the timescale, it simply gives up somewhere around a number with so many zeros, it might as well be written as a bedtime story for atoms. But eventually, even if eventually is so distant, it makes today look like the universe's first morning. These behemoths will lose mass, shrink, and emit their final bursts of ghostly radiation before disappearing entirely. Their last moments will be quiet, almost tender compared to the violent lives they once led. Smaller black holes will evaporate sooner, though sooner still means longer than galaxies have existed. In their final stages, they will release their remaining energy in brief, faint flashes, tiny cosmic sighs marking the end of their long, patient existence. After that, no black holes remain, and with their disappearance, the universe will have lost its last active participants, leaving behind only cold particles, stretched space-time, and the memory of a cosmos that once crackled with light. Yet there is something deeply poetic about this ending. Black holes, which began as the ultimate consumers, end their lives by giving energy back to the universe. They return what they once took, drop by drop, until nothing remains but the space-time they once shaped. In a cosmos that grows increasingly silent, they become the final storytellers, leaving behind a faint glow that lasts long after every star has dimmed. The future of black holes is a story of patience, endurance, and transformation. They outlive the galaxies that host them, the stars that feed them, and the environments that shaped them. And as the universe drifts toward darkness, black holes remain the last actors on a fading stage, changing, shrinking, radiating, and finally stepping down only when there is nothing left for them to influence. They are the universe's final heartbeat, the last dynamic process in a cosmos settling into eternal quiet. At the end of this long journey, from the birth of black holes and collapsing stars to their patient growth, their dramatic outbursts, and their unimaginably distant futures, one question lingers like the last glow of a dying galaxy. Why does it feel so natural to describe black holes as if they are alive? They do not breathe, they do not reproduce, and they certainly do not spend afternoons sunbathing on cosmic beaches. Yet the metaphor persists because black holes behave in ways that mirror life far more closely than any cold, silent patch of warped space-time has any right to. They grow, they change, they sculpt their surroundings. They respond to what the universe gives them. In a cosmos that is enormous beyond comprehension, black holes stand out as participants, shaping the grand ecosystem, even though they abide by nothing more than the strict rules of physics. Calling black holes alive lets us understand them through a lens our minds are naturally wired for. Life, after all, is not just about biology. It is about processes that unfold, patterns that repeat, and systems that adapt to circumstance. On Earth, we recognize living things by their ability to change in response to the world around them. In space, black holes show a parallel kind of adaptability, not with intention, not with purpose, but with a sort of cosmic inevitability. Their growth depends on environment. Their spin shifts depending on what they take in. Their ability to influence the world around them increases and decreases based on their history. This is not life, but it is something that runs surprisingly close. Consider how ecosystems work on our own planet. Forests grow thick in places with abundant water and sunlight. Deserts form in regions that receive little. Rivers carve paths, shaping the land while being shaped by it. Nothing exists independently. Everything feeds into a larger cycle of cause and effect. In the cosmic landscape, black holes behave like anchor species, organisms so influential that the entire ecosystem reorganizes around them. They gather matter in their direction. They release energy that controls the formation of stars. They merge, creating new structures that ripple outward into the universe. They even experience long spans of dormancy, followed by sudden bursts of activity. Their behavior, if we dare call it that, shapes the architecture of galaxies. And yet the beauty of the metaphor is matched by its limit. Black holes are not conscious. They do not make choices. They do not seek out growth or interaction. These things happen because the laws of physics demand it. But this lack of intent does not make the metaphor useless, quite the opposite. The metaphor reminds us that the universe is not a static void. It is dynamic, interconnected, and full of cosmic phenomena that behave in ways far richer than the simple models in textbooks. By imagining black holes as living entities, we open ourselves to describing their behavior with the nuance and narrative clarity that such a comparison offers. It also helps bridge the emotional gap between human experience and cosmic scale. Black holes are intimidating. They represent the extreme edge of physics, a place where light cannot escape, and where equations buckle under the weight of infinity. Yet by giving them traits we associate with life, growth, adaptation, influence, we make them less alien. We make them characters in the universe's story, not just mathematical abstractions drifting in the dark. In doing so, we create a connection, however metaphorical, between ourselves and the deepest workings of the cosmos. This metaphor becomes even more powerful when we consider how black holes evolve over time. They grow from tiny remnants into massive giants. They respond to their surroundings by spinning faster or slower. They change their behavior depending on how much material they receive. They interact with galaxies, shaping their evolution. And in the far distant future, they slowly fade, returning energy to the universe in a final act of transformation. If the timeline of a black hole were compressed into something closer to our own, it would look remarkably like the life cycle of a long-lived organism, one that undergoes childhood, maturity, influence, aging, and eventually a quiet end. Framing black holes this way also sheds light on our own curiosity. Humans have always tried to understand the unfamiliar by comparing it to what we know. We describe galaxies as islands, nebulae as nurseries, and stars as engines. These comparisons are not literal. They are bridges that help us walk from the familiar into the surreal. Black holes, with their complex behavior and their evolving influence, practically invite metaphor, a cold, silent void that grows, affects, reshapes, and transforms the universe around it, needs a framework of understanding, and the language of life provides one. In a way, the metaphor does something even deeper. It reminds us that the universe is brimming with processes that dwarf the familiar boundaries of biology. Life on Earth is just one expression of change and adaptation. The stars, galaxies, and black holes form their own grand patterns, vast, slow, and governed by forces that will outlive every molecule that makes us who we are. When we describe black holes as alive, we acknowledge that the universe is dynamic on a scale so immense it challenges every human assumption about stillness and permanence. Ultimately, calling black holes alive is a poetic gesture, a way of honoring their place in the cosmic order. They are not life in any traditional sense, but they are undeniably active participants in the universe's ongoing story. Their growth shapes galaxies. Their influence spans light years. Their evolution continues long after stars have died. They are the silent giants that give structure to the cosmos, the steady hands guiding the flow of matter and energy on a stage so vast it defies imagination. So as the universe stretches onward, as galaxies drift apart and stars fade into memory, black holes remain as reminders that even in the deepest darkness, processes continue, change unfolds, and the story carries on. They may not be alive, but they act like the heartbeat of a cosmos that is far from still, far from quiet, and far from done surprising us.